Hi ladies and gentlemen, this is Mr. Green and this is my pre-cal class connect time, and I recognize I should be here with you guys, but they have me scheduled to do a testing today, so I am out of the office and not able to be with you. So I apologize about that, but that's the way life goes occasionally. What are we doing? You should be working on Unit 3 material. Unit 3, and you should be doing some harmonic modeling type problems. Difficult things. I covered a couple of them in the last Class Connect because I knew I wasn't going to be here, but I'm going to cover a few more today just to make certain you know what's going on. Remember, after 28 days, we close down things, so you want to make certain you got everything taken care of and there are no zeros out in that grade book because that's going to hurt you the most. So, what do you mean by harmonic modeling? Well, when you're looking at a harmonic thing, one of these types of problems, which is a sine, cosine, trigonometry type problem, okay, it's usually some sort of a motion that is moving back and forth, back and forth, back and forth. And you just want to make certain that you can be able to model that. Speaking of which, you know, I found a video that I thought you guys might find kind of interesting. So I'm going to play the video now, and hopefully it'll come across to you guys real closely here. This is a video. It's using water and sound. Sound makes harmonic waves, right? The water is going to show you what's going on. Look at what they're doing here. They're taking a speaker and some rubber hose, and they're going to secure the water source, and they're going to make a tone generating software that'll produce a 24 hertz sine wave. That's 24 uh, feet per second capable camera, frames per second capable camera. That's 24 frames per second capable camera. That's what they're using there. Okay, so you got to watch what goes on with this water when they do it. Oh my goodness, the sound waves are hitting the water and causing the water to make a sine wave, to show that sine wave. It is amazing that they are able to do that. Okay, they're going up to 25 megahertz. What do you think is going to happen? Interesting question. Let's look. Oh, it shows the sound wave moving. Look at that. Why is that? Because the camera's at 24 frames per second, and the waves that they're getting are at 25 frames per second. So it looks like it's progressing forward, and it's moving down a little bit there. If they go to a slower frame size, it would look like it's actually going back up instead of going back down. I'll show you that here in just a second. It looks like it's picking the water up off the ground and sucking it in, doesn't it? It's not. It's just because of the difference between the camera and the sine wave that's being generated that it looks like it's doing that. Okay? Water is actually still falling down. Trust me. It's not defying gravity here. So, I wanted to show you all that because I found that video the other day. and I thought it would be nice for you guys to see that, okay? So here we are, we're looking at this one here, this problem here. It says to find the period. Well, we know that the period is represented in this area right here, right? Right there. So what we have to do is we take the 3 pi over 4, and we say the normal period is 2 pi. So what we have to do is since this is the frequency that we've just written down here, we have to invert it. That's 2 pi divided by 3 pi over 4. Well, the pi's are going to cancel each other out, so that's going to go away. And I'm dividing by a fraction. The way you divide by a fraction is you invert and multiply. So that becomes 2 times 4 divided by 3, or 8 over 3. The period is 8/3. That's how you find the period. It's really that easy to find them. It's not like it's the rocket science that we're doing here. Well, you know what? It is kind of rocket science, but it's not like it's that difficult to do. Okay? So what we did there was I took 3 pi over 4, divided it by 2 pi. That's the frequency. So the period's the inverse. Flipped it over, used my math that I needed to use. That's 2 times 4. Pi's will cancel each other out. 2 times 4 is 8 over 3. That's how I got that information. Okay? Now, one of the problems that seems to be giving some people some questions is, how do you find the length of a pendulum? Well, a pendulum is nothing more than a stationary rod with something at the end of it. Okay? You've seen them, grandfather clocks. They tick back and forth. Tick, 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 right? Well, this one has a period of 10 seconds. What does a period mean? That means if it started right here, it went here, back down to here, and back down to here. It took it 10 seconds to get to that point. That's one full cycle of the whole thing. Well, the period is equal to 2 pi over theta, or 2 pi times the square root of the length of the pendulum divided by the gravitational force. So all we have to do is stick that 10 in here and set it equal to 2 pi times the square root of L divided by 9.8. Where'd the 9.8 come from? 9.8 is the gravitational constant. So I can now divide by 2 pi, and I'm going to get 5 over pi is equal to the square root of L divided by 9.8. You know, square roots, I don't like those. If we square both sides of the equation, it goes away. 25 over pi squared is equal to the length divided by 9.8. I can multiply by 9.8, and I get 25 times 9.8 over pi squared is equal to the length. That's how you go about getting that. So here's a calculator. I'm going to clear my screen here. Thank you. Clear. Good. So I'm going to say 25 times 9.8 divided by, and I'm going to use the exact value for pi as my calculator can go, pi squared. And I'm going to get 24.82. Now, I know some of you will be out there going, but don't you just use 3.14 divided by parenthesis 3.14 squared parenthesis, and I want to show you the difference between it. I got 24.85, and this one was 24.82. I wanted 5 because I'm rounding up because of the 8. Okay? So it's off by about 3/100ths there. Okay? That's why we always say that pi is an approximation. Okay? So this length should have been 25.82 would have been the answer that should have been given. 24.82. Okay? That's the answer you should have been given. Because we weren't told to use 3.14 up here, were we? So that's why we used the exact value pi that my calculator would do to give me this number, 24.82. Cool? And it is an approximation because even at that, it's an approximation. It could be anywhere between those numbers. 24, 8, 20. I got 25 there. Why am I got 25? 24 is what it's supposed to be. Okay, 25, 25, and this is 24.82. Okay? So, approximately. Could it be 24.845 in between there somewhere? You know, we're talking about a hundredths of a meter at this point. So, it's not a very big distance. Okay? We're talking about a millimeter. I'm sorry, we're talking about 1 centimeter at this point. So, we're talking about between that 3 centimeters. Could 3 centimeters make a difference? In seconds? Yes. Okay? And you got to be very, very accurate with it. Okay? Okay, going forward. This is a problem I pulled off of a quiz from Unit 2 because I had several people that were getting this wrong, and I wanted to just show you my simple way of solving this. Okay? I'm bringing up a calculator here, and I'm going to press y equals. And in this y equals, I'm going to just say 3 cosine x, close my parentheses, plus 2. Hit enter. I'm going to graph it because I want to make certain it's working correctly. And my graph is just giving me a straight line. So what I have to do is I have to do a zoom, make certain it's giving it to me as a trig function so that it looks like that. Now I got a nice little cosine wave there. I want to make certain that I'm in radians, and I'm not. So I'm going to make certain I'm in radians. Okay. And now I'm going to hit graph again just to make certain it looks right. Nope. Now I get this wiggly, 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 wiggly. Well, that means I need to go back and zoom it to trig again. Zoom, trig, and it'll give me this nice little cosine wave. Okay, that's 3 cosine. You see the 3 here? That's causing it to be 3 times taller than what it would normally be. And the 2 at the end, here, causes it to be shifted up 2 units. That's why it is up 2 units higher than what we would normally expect it to be. Okay? So what I'm going to do is I want to take each one of these other problems here and put them in as y2. So we're going to say 3 times the sine of x minus parenthesis pi, shift pi, divided by 2, parenthesis, plus 2. And I'm going to graph that. When I graph that one, you can see it doesn't line up with the other one. Matter of fact, it's off considerably there. So it's not going to be that first one, okay? So I'm going to come over here and I'm going to mark the first one off. Not going to be that one, okay? So let's try the second one. I'm going to go down here again, and I'm going to say negative 3 cosine of x minus 2. And then everything else goes away. Oops. I left a parenthesis off there. Parenthesis minus 2. And if I graph that, there's the original graph going back up there again. And now here's the new one. And, you know, besides being able to put little eyeballs in there, and it's looking back at you, doesn't look like it's the same graph at all, does it? So it's not going to be that second one. Okay? Okay. Let's go ahead and try the third one then. So y equals, we'll go down here, we'll clear that one out. We'll say 3 cosine of a negative x, parenthesis, plus 2. And we graph that one. And here's the original graph going on here. And wait a second, I don't see anything happening. You see the little thing up here in the corner that says it's still thinking about it, but no new graph showed up. I wonder. So what I'm going to do is I'm going to press second graph. And I'm going to look at the values here. And look how they line up exactly. My y's are the exact same values here for these values of x. So that must mean that it is the same graph. Okay? So that means, yes, that one's a good one. I'm going to check that one. Good. Okay? So now we want to try that last one because it does say check all that apply. So I'm going back to here. I'm going to clear out that answer there. And it's 3 sine of x. Sorry, had to cough. Didn't want to cough in your ear. 3 sine of x plus pi divided by 2, parenthesis, because there's two parentheses there, plus 2. And I hit graph on this one. There's my original graph going in. And just like that other time, I see the cursor moving up here, but it's not showing me any new graph. So I'm going to press second table to look at the table values, and once again, they line up perfectly. They're exactly the same. So that means, yes, that one is an exact match for it too. That is the way I like to do these with the calculator because it does help me do them, okay? And it will show me if they're exactly the same. Okay? Okay, well, that's all I've got for Class Connect. I would have more if I were with you, but I'm just, can't be there right at the moment. If you have questions about the things you're doing with harmonic motion, watch last week's Class Connect, watch this week's Class Connect. Come by and talk to me in the tutoring session on Tuesday, Wednesday, or Thursday. Well, today's Wednesday, so on Thursday, and we will see what we can do, okay? Secret word for today is free throw, and if you are watching this video, you need to send me a K-mail telling me that you watched the video and the secret word is free throw, okay? I appreciate you guys telling me that you're in pre-cal every time you do things because it really helps me find your records and respond to you in an appropriate manner. I'll talk to you next time.